Okay, hi everybody. Today we're going to be going over all of the answers that you and your group mates should have gotten for the alkenes worksheet. So let's take a look here. First question was explain based on the appropriate IMFs why the melting points and boiling points of alkenes and alkynes are so low. So the first thing I would do here is I would make sure that in fact I could explain based on the shapes we see. So let's just use ethene and ethyne. So if I have ethene, I basically have this sort of format. And if I have ethyne, then I basically have this sort of format with quite a bit less surface area. And the only real difference other than a small amount of mass difference, and so the mass difference is pretty much negligible because it's a difference in two hydrogens. And what we have instead is ethene has more surface area, so it has greater London dispersion forces, so it has higher boiling points. Okay, now why are there, in general, why are their boiling points so low as compared to the alkanes? Alkanes have more, even more surface area, so more LDF. Okay, so that's going to be our reasoning for what is affecting those melting points and boiling points there. Okay, so let's go ahead and go on down to the next couple questions. Explain why the double and triple carbon bonds are, carbon-to-carbon bonds are planar, while the single bond, the C to C single bond, is not. So let's just keep in mind that what we have around each of the carbon double bond is a trigonal format, which is a trigonal planar format, and the carbon-to-carbon triple bond is a linear format, which are both in the same plane, but an alkene has more of a tetrahedral format around each carbon. So you needed to have answered that the electron geometry around each carbon is tetrahedral, which is exists outside of a single plane, whereas these are both planar molecules, as in trigonal planar and linear shapes. So you needed to answer this in terms of their Lewis dot structures around each and their molecular shape around each carbon. Okay, so let's go ahead and go on. Write the IUPAC name for each of the following compounds. This first one is a 1, 2, 3, 4 alkene with a methyl group. So this should have been named instead 1, 2, 3, 4. So this should have been 2 methyl butene. And then this one, and I spelled butene wrong, there we go. And then this one has the double bond here, and it looks like I'm going to need to see what else is here. Okay, so that I've got to count my carbons. So I've got 1, 2, 3, 4, 5, 6, 7, 8, and I have a methyl group on 5 and 6, and that just made it clear to me that I named this one wrong. No, I named that one correctly. This should be 2. I'm rethinking that. Okay, so if that's the case, I have 3 methyl groups, and they're on the 4, the 5, and the 6 carbon. So, and I should have, I did name this wrong. This should have been 2 methyl 2 butene. Okay, so there's that. Over here, I do have a 2 octene, but my methyl groups are on the 4, 5, and 6 carbons. So here we go. We have 4, 5, 6 trimethyl -2 octene. Okay, and then this one I have two bromo groups, and so I'm going to count my carbons from where the double bond is. So I have 3,4 dash di bromo, and this is going to be dash, you can either just call it cyclohexene, or you could call it 1-cyclohexene. Either one of those would be fine. Okay, on we go to the next part, still naming these, so let's continue with that. This one is going to be an Y and E because of that triple bond here. So there's our 1, 2, 3, 4, 5, and 6. So I have a bromo group and I have a methyl group. So I have 4 bromo dash 3 dash methyl and dash 1. I can show the 1 if I want to. I don't have to. Hexine there. Okay, so this next one, my double bond is closest to this end. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and I have a chloro group here and here. So I have a 4, 5 dash dichloro, and my double bond is going to be on the third carbon, 3, and that is a nonene, just like that. Okay, and my last one is going to be, there is no double bond involved here, so this is just a cyclopentane. So this is a cyclopentane, and I just need to say where the chlorines are and where this extra thing is, and that is an ethyl group. And these are chloros. So we're going to start from the chloros because they alphabetically come first. So this is 1, 2, 3, 4, 5. So I have 1, 1 dash dichloro dash 2 dash, and then we have to put the ethyl cyclopentane there. There we go. Those are our names. Okay. Going on then. We have, write the full or condensed structural formulas for each of the following compounds. Okay, so this is a cyclohexene. So let's go ahead and draw in our hexene. And there it is. And then I have a 1 iodine and a 2, 3, 4 iodine. And so there it is, 1, 4 diiodo, 1 cyclohexene. Okay, and then I have a 2 bromo, 1 iodo, 3 methyl cyclopentane. So cyclopentane just looks like this, no double bond, and I'm going to have an iodo at the first one, and then I'm going to have a methyl group at the third one, so CH3, and then I'm going to have a bromo group at the second one. So that should be what we drew there. Okay, moving on. Then I have a cis-2 pentene, and I want to make sure that I do this right. That means I'm going to have 5 carbons, 1, 2, 3, 4, 5, and there is the double bond in between the second and the third pentene, and I'm going to need to make sure that I show my my 2 parts of the pentene on the same side of the double bond. That means that there is going to be a H here and a H here, with the rest of these all having their H's, of course, showing just like this, and that should be what you got. So the H's should have been on one side with the other parts on the other side. That's our cis-2 pentene. Okay, so the next part then, look at the structures for 6-dodecene below. Which one has a trans double bond configuration and which one has a cis double bond configuration? How do the configurations affect the overall shape? So this is our trans, and this makes more of a, it appears like more of a linear shape overall molecule, and this is our cis, and this is more of a bent shape overall molecule. Okay, so then we are going to go on to complete the following reactions. And so the following reactions need to be able to be let me go. Okay, so completing the following reactions, we had to be able to determine which one to put the asymmetric water onto. So I chose the secondary carbon for the hydrogen to go on, and I chose the tertiary carbon for the OH to go on. That was following Markovnikov's rule. And then on here, the double bond was symmetrical, where on both sides was a secondary carbon. So, and the Br was also symmetrical. So I just had to break the Br's bond and put it on there. Okay, so let's go on to our next one, and I'm going to erase that. And so looking at our next two, we are wondering now on this one, what were the reactants? So you know one of the reactants is HCl. So it's basically asking what was the alkene here. So because I know an H gets added and a Cl gets added, and the Cl has to be added to the carbon that is more, I guess, more inactive or more stable. So the Cl goes on to, and both of the carbons actually end up being secondary. So it's no difference. They're both asymmetric, so, or symmetric. I'm sorry. So we should have had CH3 bonded to a CH, which was double bonded to a CH and a CH3. So that was 2 butene. And so this next one, then we have an alkene that this is going, sorry, an alkyne. So what we're going to have is a Cl, and we're going to break one of the bonds. We're still going to have a double bond, but we're going to have the H add itself onto here and here, and then that is still added to the hexane just like that, or the cyclohexane. Okay, so we're going to move this along to our next one. Now we're going to draw the products, label the major and minor products of the reaction between 2-methylbutene, 2-butene, and each of the following. So I'm going to do each one, and then I'm going to erase and do the next one and so forth. So the next one I'm going to start with H2, and we're going to be adding in, drawing in the products of the major and the minor here. So what we have here is 2-methyl CH2, CH3, and the C with the methyl group attached here. And then we have the double bond here. And I do have to draw it out because otherwise I cannot envision what this is going to look like. So there is my 2-methyl 2-butene right there. And to that, I'm going to add some hydrogen. So when I go and add my hydrogen, this bond is going to break, and then my hydrogen is going to get added on here and here. And I don't have a Markovnikov's rule, so this is the only product. So this is the major product. Okay, so that was for A. So what about for B? Let's go take a look at how does this look for B. And B, we're going to be adding on an asymmetrical water. And so that is going to be asymmetric added to asymmetric. So again, we are going to break the double bond, but now I have one tertiary carbon, which is where the OH is going to go, and I have one secondary carbon, which is where the H is going to go. So I'm going to put them there like that. The same thing as A happens with C, in that we have a symmetric Br2. And so since we have a symmetric Br2, each Br is simply going to get added on to the 2 carbons of the double bond. So we end up with that. And then we have, finally, we have the, oh, I did not want to do that. Hang on. All right, so I'm going to go back. And then the last one you should have gotten was that we would break the double bond, and the H still goes on the secondary carbon, but now the Cl goes on the tertiary carbon, just like that. And that would have been how we did each one. Now, this one will have the, that's the major product. The minor product would be where these two are switched. And the same thing would have happened for the OH and the H of the H2O. So this particular one is the major product. The minor product would have been where you have the chlorine on the other carbon, the secondary carbon. Okay, so now we are going to go on to, oops, the last part here. Is this our ending? This is our ending. Okay, yay us. So now we have the starting, we want to know what the starting alkene or alkyne and the other reagent used to for the following major products. So, oh boy, we have to figure out what the reactants were. So if this is 2-chloro, and I'm going to have to draw all of them out, this is 2-chloro-3-methylbutane. So we have a butane, just like this, and we have a chloro group on the second carbon, and we have a methyl group on the third carbon. And this is what this looks like, just like this, H here, and H here, and a CH3 here. That's what that is. And so that means that we would have had, this is the following major product. So I would guess that what we had that came from this was probably a HCl. And then we have, now there might be more than one correct answer. You might have said that there was H2, in which case that would have been a different reactant. But you might have said that there was an H2. I'm saying there was an HCl. So that means this Cl and this H would have come off, and I would have been left with CH3, CH, double bond, C, methyl group here, and then CH3. So that would have been one way to do it. The other one would have been to have the Cl and the CH3 already be there, and the two H's would have come off there. Okay, so let's go try the next one. How do we form 3-hexanol? So if we have 3-hexanol, so there's our hexane, and let's just say that this is where our OH to make the alcohol is formed, making this 1, 2, 3, 4, 5, and 6. And so to make a alcohol, we know that water is one of the reactants, and we also know that then there has to have been a double bond in between here and here. So we would have had that right there, and then we would have added in the H, which is going to go right in here. That's where the H is going to go, and that's where the OH is going to go right there. And we would have been able to argue that those two carbons were equal to each other in symmetry, so it wouldn't have mattered which side we put it on. So there's that. It does make me wonder, based on how this is labeled, if this was already a if this instead, and I am rethinking this, I'm thinking, boy, I can't draw that. Let's try that one more time. I'm thinking that this was already a double bonded alcohol. So the double bond would have been right here, and we would have had the alcohol coming off of here, more like this. And that instead what we probably, so yep, that's what I'm thinking. What we probably would have added was an H2, which would have given us that hexanol of our choice. So this is going to be what I think you should have come up with for that one. Okay, so how do we make 1-methyl cyclopentan 1-ol? So the cyclopentan 1-ol, there's that, and the so that means, let me go ahead, that means I have a alcohol there, and also at that same point I have a methyl group there. Okay, so cool. Let's see if we can figure out what came from that. So we know some water came from that. We could also say that possibly that this would have had to have been the double bond right here, with that being the first carbon 1 and carbon 2, which means our methyl group would be already sitting there, and that we would instead break this double bond to form this, sorry, that should be this way, breaking the double bond to put on the H over here and the OH right there. And that does make sense for Markovnikov's rule and the major product. So that's what we should have come up with there. And then the last one, how do we make 2-methyl propane? So here's our propane, 1, 2, 3, and the methyl group right here. And this would tell me that we're probably just adding, so that's a CH3. There probably was a double bond right there, and that was a CH2. So if we were going to make 2-methyl propane, then this would be what we are adding the hydrogen to. And then when you break that double bond, you would end up with CH3, CH with that methyl group still attached there, and then CH3, just like that. So those were our answers for this. Thank you, everybody. ahead and pause this for right now. Here.